Good morning. Assalamualaikum. So today we will start chapter 3, which will be covered in your midterm. Okay, chapter 3 is regarding separation train synthesis. After your process gone through the reaction in reactor, so your effluent product most of the time must be separated. Okay, because it will consist of mixtures, perhaps your unreacted reactant, products, byproducts, catalysts. So from there, you will need to separate. So the chosen separation system is depend to your effluent, your product stream. Okay. So in this chapter, we will cover the criteria for selection of separation method. Okay, selection of equipment, which separation equipment that you need to use. Okay, then how to sequence the ordinary distillation column for multi-component mixtures. Okay, for the sequencing, we focus only on the ordinary distillation column. Okay. Now, just to recall, we had done in previous chapter, part 1, part 2, initial part and part 1. Now we go for the detailed process synthesis, which involve the separation part. Okay. As you can see over here, this PFD from the feed into the reactor. This is always your main major equipment, okay, your reactor. So after the reactor, you have your product. Reactor effluent, then from here you will have mixtures, mixtures of products. As I mentioned earlier, byproduct, main product, unreacted reactant, catalyst, waste. So you need to separate them. How to separate them and the purpose to separate them. Okay, the purpose for the separation process, you can find it here, to purify a reactor feed, recover the unreacted species for recycle to a reactor. Okay, if it is feasible to recycle. Okay, then separate and purify the products from a reactor. This is the general purpose for the separation process. Okay. Okay, where separations are too difficult, purge streams are used to prevent the build-up. Okay, this one we had discussed earlier on the separation heuristic, right? There are three cases for the separation. Okay, then for binary mixtures, may be possible to select a separation method that can accomplish this just in one piece of equipment. Okay. Okay, this one is for general binary mixtures. Binary mixtures, you can have azeotropic mixtures, miscible mixtures. So from there, you can investigate in detail what are the suitable equipment. Okay. Now, phase separation of reactor effluent. There are few phases commonly produced after the reactor, okay, in the reactor effluent. So here assume this feed is from reactor. Okay, from reactor, then goes into the separator. Okay, in this case, flash. Okay, we have flash over here, we have decanter, centrifuge. Okay, depends. Now we have vapor liquid mixture. We can also have vapor and two liquids mixture. Okay, in general, vapor liquid. This one is also vapor liquid. Here is liquid liquid. Okay, liquid liquid mixture. Slurry. Slurry mix of solid and liquid. Solid, liquid, slurry. Okay, so these are the possible phase condition. You will come across a few types of possible condition. Okay, vapor, solid, vapor, solid, liquid. Okay, you can even have the three phases: vapor, solid, and liquid. Okay. Your PDP, have you sketched your BFD yet? PFD. Then, so far, what is your product after the reactor, the phase? After your reactor, your main reactor. Phase of the product. Liquid, liquid. Mixtures of products. Liquid, liquid lah. Okay, so liquid, liquid. Okay, so the effluent from the separation usually sent to storage. If you already have your high purity of product, can straight away send to the storage. Okay, if you have byproduct, and then perhaps you can recycle the stream. Okay, then separation of the recycle stream. Okay, from here, this is the reactor effluent. Okay, in this BFD, it involves few separation system. Just after the reactor effluent, just after exiting the reactor, we have one phase reaction over here, phase separation. Okay, here it separate the phase first, vapor, solid, or slurry. Okay, vapor go up here. So perhaps here vapor, mixtures of vapor. So you separate the mixtures of the vapor phase. If it is possible to recycle, okay, you can recycle back to your reactor. The rest perhaps can be your product and or byproduct. Okay, if there is any low concentration, so you can push it up to avoid the build-up. Okay. Then for the solid or slurry stream over here, we'll go to another separation system where it separates the liquid and solid. Okay, solid, if it is possible to recycle, then you can recycle. Okay, this is not a fixed BFD. It depends to your system. This is for example. Okay, and then from here, it separates the solid and liquid. So liquid go to here. Liquid. So perhaps here have mixtures of liquids. Okay. So after going through a few separation system, you will have your products. Okay. So as overall, this is your input. All these effluent stream is your output. Okay, again, it depends to your effluent, reactor effluent phase. If you only have vapor phase, then choose the separation equipment that is suitable to separate the vapor. Okay, up to there? Can I? Now we go for this one example where you have to consider the synthesis of a separation system for the recovery of butenes. From C4 concentrate from the catalytic dehydrogenation of N-butane. Okay, so here the reactor involved. Okay, here is your reactor. Feed here is your N-butane. N-butane. So the reactor effluent is all these things. The process feed, okay, which contains process feed here means the reactor effluent, which contains all this. A until F. Okay, here is A until F. Now, this reactor effluent is the feed to the separation process. Okay, so here we have 5 components to be separated. Your main target is to recover the butenes. Your mixture, you have a few. Propane, 1-butene, N-butane. This is unreacted reactant. Okay, the C, unreacted reactant. You have trans-2-butene, cis-2-butene, and N-pentane. Okay, so your target is to recover butenes. Means B, B, and E. Butenes. How many carbon butenes? Butenes. 4. Single bond, double bond. Double bond. Okay, butenes. Huh? Now, target is to recover B, B, and E. Okay, here. This is the requirement from the question. Now, how to separate them? You have 5 components to the feed with this rate, okay, kilomole per hour. Now, you need to find out the properties for each component in order for you to separate. The important properties is their boiling point, critical temperature, and critical pressure. So that you know to manipulate the condition of this separation equipment. Okay, can I? Again, I repeat, you need the properties of the boiling point, temperature, pressure. Critical temperature, critical pressure. In order for you to manipulate the separation equipment condition. So from these properties, you can know which will be your distillate, which part will be your bottom. Okay. Now, there are two separation methods proposed over here. Distillation and extractive distillation. What are the difference? Distillation and extractive distillation. You have a few more types of distillation. But for these two, what are the difference? Okay. Which type? Correct. Yes. Extractive is with the presence of solvent to help the separation process. Most of the time when it involves azeotropic or miscible mixtures. Okay. Distillation, the number one over there, the general distillation system. Okay, what are other type of distillation? Other type of distillation column that you know? Distillation column, the type of distillation column. What else? Type of distillation column other than this extractive. Okay. Yes, fractional distillation. What? Yes, reactive, which we had gone through in previous lectures. Others? How about others? What type of distillation? No more. Huh? PSA. What is PSA stand for? Pressure swing adsorption. One kind of distillation, if you read through, it is one type of distillation as well. Sure. Other than that, thyrogenic. Thyrogenic. Other than that, what else? Okay, you can read through lah. If you Google, there are few journals or few websites that state few types of separation. In your PDP, you use what type of distillation? In your PDP? Simple distillation and extraction lah. Okay. Other group? What do you use? Type of distillation. Other group? Jin, how about you? Now I know your name. What type of distillation column your group use? Same group ah? Do you use distillation column? PDP. No distillation column. Good. What type? Not sure. Fractional distillation. Commonly used is fractional lah. Okay. Okay, later we will go the ESA and MSA type. Yeah, later we go to that. Now we proceed with the example. Okay, I want to highlight on this how it separates few distillation system, few separation system, in order to focus on recovering of the butenes. Okay, okay, here the main feed. This is the main feed just now that consists from A to F. Okay, here A to F. Okay, the main feed. Now it enters the first separation system, where over here C3 and 1 butene is in the distillate. C3, 1 butene in the distillate. Okay. Now you have two components which you need to separate further to extract out the 1 butene. Then it goes to another separation system. Okay. Then you will have your butene and propane from this sequence. Okay, this sequence you get propane, C3 and 1 butene. Okay, up to there. Now, the first sequence, distillate is C3 and butene. C3 and butene. Propane. A and B, 1 butene. A and B. Okay. So the bottom product, what could it be? Distillate is A and B. Bottom? Bottom here? The rest ah? Right, C to F. I highlight. Okay, bottom here. The one that enters to the next separation system. Okay, so here it consists of C until F. C until F enters the second separation system. Now from here, okay, focus on the notes over here. NC4 and 2C4. NC4 here is the C and butane. Okay, NC4, C. 2C4 is what? The trans and cis butene, D and E. D, E. 2C4. 2C4 here, trans 2 butene and cis 2 butene. Okay, cannot be separated by ordinary distillation because their relative volatility is 1.03. Okay, the relative volatility, it represents the ease of recovery. The larger the relative volatility, yeah, the easier the component can be recovered. So here, small value of relative volatility. So this CDE is hard to separate. Okay, so that's why 96% furfural is added as an extractive agent. Okay, so now you see the relative volatility increase from 1.03 to 1.17, slightly higher to ease the separation. Okay, now furfural is the agent. How to choose this agent? It depends to its own properties. And the main thing, make sure it is not reacting with the component. Okay. Now, so this second separation system, okay. This second separation system is using extractive distillation. Because the CDE is hard to separate. So they use extractive separation, extractive distillation. Okay. Now the pentane is the bottom. Okay, pentane is the bottom over here. This is a N-butane, right? N-butane. Okay, N-butane is the distillate. C, D, E, F. Okay, so C, N-butane, release over here. C. Pentane is the F. F. C, F. Where is DE? Okay, DE just now, because it is hard to separate, we add the furfural here. So furfural, D and E, two butenes, D and E. Here, D, E, two butenes. Now here is D, E plus the furfural. Okay, it goes to the next separation where it separates the furfural and the DF, the butenes. Okay, so here the furfural being recycled back to C4B, distillation over here. Let me write it nicely so that you understand. Okay, here's C. Sorry, not C. Here is D, E, and furfural. Then the one that being recycled back is the furfural. Okay, now you have recovered your main target, D and F, which is, sorry, not D and F, D and E, sorry, D and E. D and E, the butenes. Okay, 5 minutes for you to digest this separation system. How it flows, what to be added. Any question on this slide? Anna? Now, for the separation, again, it depends to the chemical composition of your feed. Okay, the differing chemical composition will result in different method of separating system. Okay, now here there are 4 common industrial techniques. Now the first one, they use energy separating agent, where it the components are separated by difference in volatility, thus causing each species to favor one phase or another. So you play around with the energy in order to push them to change the phase or other way. Okay. ESA, the term is ESA, energy separating system, separating agent. Second one, introduce a second fluid phase. which is MSA. M stands for mass separating agent. The ESA, energy. Okay, so the furfural just now, this system, it used MSA. Furfural is the MSA, mass separating agent. Okay, MSA. Okay, the solvent selectively dissolve or alter the volatility of certain species of the mixture. Okay, it usually recovered and recycled. Similar to the furfural here. It is recovered and recycled to the next, to the previous column. Okay. So here again, the furfural is the MSA, mass separating agent. The third method is the addition of solid phase, upon which adsorption can occur. Okay, so here you add solid phase so that the separation occurs in adsorption process. This one, the PSA, pressure swing adsorber. Okay. The fourth technique is the placement of membrane barrier. Separate them using the membrane. Okay. Now the membrane barrier separation process. What is the concept of the separation process over there? Distillation, we base on different boiling point. Membrane, osmosis, pressure. Correct? Other thing that you need to consider? Particle size, yes. Particle size, the solute size. Okay, the membrane, it plays along with the pressure, the osmosis, and also the particle size, the solute size. So membrane over here, does it work with liquid-liquid solution? Liquid-liquid separation for membrane. Will it work? Will it work for liquid-liquid separation? Don't know, no idea. Just now you mentioned membrane, pressure, and particle size. Right? If you have two different liquids you want to separate, will membrane work? Aisha, how about you? When you have two liquid mixtures, I say two liquid mixtures, will membrane works to separate them? No or no idea? Sorry? You don't think so because? Two different flow rate? Two different? Okay, two different liquids. Okay, how about the rest? Gwendolyn, will membrane works to separate two liquid mixtures. Jubaya, how about you? What do you think? Possible? Possible or impossible? Possible. Okay, I just want to know your opinion. I will explain later. Is it possible? Possible, huh? Your answer is possible. Next week is Dialan. How about you? Possible. To separate two liquid mixtures. Because of different density. Okay. Clement, how about you? Because?
Yes.
Just no, okay? Damien, how about you? No, because? Not sure. Okay, as I mentioned just now, membrane, the concept is, as you shared, it involves the pressure. Okay, where this one, the osmosis ones. And particle size. Particle size. When you have liquid solution, is there any solute inside the solution? It dissolves. Solute. Solute means the particle inside. And then it already dissolved. Mixtures of liquid. Okay, let's say, for example, mixtures of liquid, ethanol and water. Liquid mixtures, right? So both, we won't detect any particles inside it. So they're mixtures, liquid mixtures. So it is not possible to separate them using membrane. Membrane, it works with small solid particles where you still can see, not can see, there is still solute inside the solution. Okay. So for membrane, let's say if you have ethanol and water, liquid solution, it is not possible to use the membrane. Okay, because membrane works with particle size. It has pores, membranes, small pores. So it works with particle size. Okay, similar concept on the particle size, similar concept for the adsorption. The concept is the pore size, which involve solute. If you have, let's say, dye, methylene blue dye solution, you mix methylene blue with solution. Yes, that one you can use the membrane because you still have the dye solute which dissolve inside the water. You can use also adsorption. the pore size. Okay, the adsorption here is not only the pore size, it also works with the surface charges. Surface charge. Okay. Can you get the concept? Any question? Okay. Any question? Now, so these are the 4 common techniques. The one that I want to highlight now is technique 1 and 2, the ESA and MSA, how to use it. The MSA, as the previous one, peripheral. Okay, this is one of the example. Now we can look into another example. This one you can read through the common industrial separation method. There are a lot more separation method involved in the industry. Okay, crystallization is one of the separation method as well. It separates what? Crystallization. What phase? Solid and liquid. The feed is solid and liquid, so main product here would be the solid. Okay. Now here, criteria for selection of separation method. Which one to be used? It depends to the feed condition. Either vapor, liquid, or solid. Okay, so if vapor, these are the common techniques for the separation. You can do partial condensation, distillation, absorption, adsorption. What's the difference? AB and AD. Absorption and adsorption. What's the difference? Ab. What's the difference between these two? Okay.
Absorption of bulk phase.
Involve bulk phase. Adsorption on the surface, yes. Adsorption on surface only. Absorption, it pass through. Bulk phase, yes, in bulk phase. Pass through. Sorry, not phase, pass through. Pass through surface. Okay, adsorption, for example, we have this. So your solution your solution can pass through. Pass through. It pass through. This is adsorption. But if adsorption, it plays on the surface, the solute particles attached on the surface. Okay, the solute attached on the surface. Adsorption. Absorption, it pass through. The solute pass through the film or whatever that you are using. Adsorption on the surface only. Okay, it attached on the surface. Okay, so in in the separation method selection, we need to consider the separation factor. Okay, which it defines the degree of separation achievable between the two key components. Between the two key components, degree of separation, similar to the relative volatility just now. Okay, from the equation over here, the formula over here, you can see separation factor equivalent to the relative volatility of the component. Okay, relative volatility high, easy to separate. If relative volatility low, hard to separate. Okay, this relative volatility, it involves between two components. Let's say just now, here you have 5 components. So the relative volatility, it involves between two components. So it means over here you will have a few values of relative volatility. Perhaps you should have another column which mention the relative volatility between the components. Okay, maybe between propane and butane, so it has its own relative volatility. Butane and this, between two components. Okay, we'll go through examples so that you understand later. Now, how to find this relative volatility? It depends to the K values over here. Vapor liquid equilibrium ratio. Okay, component 1, component 2. And also it depends to the phase. Vapor, liquid phase. Okay, this one is in vapor phase, liquid phase. In thermodynamic, Y is always vapor, X is always used for liquid, right? In thermodynamic. So it always to represent similar. Y, vapor phase, X, liquid phase of each component. Okay. Okay. Now here, separation factor equivalence to the relative volatility. for vapor-liquid separation operation that use MSA. Okay, that causes the formation of a non-ideal liquid solution. Non-ideal. Because you already you add in the MSA. Okay, for example, just now the furfural being added to the D and E. Now, operate at near ambient pressure. Okay, based on the Raoult's law, this is the equation. Okay, this one for you to understand only how it relates. Okay, now if the MSA is used to create two liquid phases, such in liquid extraction. Okay, so the SF referred with relative selectivity, beta. The alpha just now is relative volatility. Okay, but when you add in the MSA, it converts into beta, relative selectivity. Because the MSA later on will help in the separation system. It change, let's say you have liquid 1 and liquid 2. MSA joined with liquid 1. So it already changed the properties for liquid 1, phase 1. From there, you can adjust the parameter, the condition, to proceed with the separation process. Okay, for example over here. Here we have feed over here. Okay, this one I extracted from this journal, this figure. Now we have over here the feed is ethanol and water. Okay, we know that the boiling point of ethanol is 78. Water is 100. Closer boiling point, close boiling point. So it is hard to separate. So you choose the extractive distillation column by using MSA. What is the MSA agent? Here is the salt. Okay, over here, salt is the MSA agent. How it works? It will increase the relative volatility of the more volatile component to the mixture. Okay, so when salt add in water, the boiling point will increase, right? If you boil normal water, you'll get at 100 degrees C, it will boil. But if you add something, salt, it will boil at higher temperature, right? Because of the salt inside it. So the salt already changed the properties of the solution. Okay, so here the salt act as the MSA added to the feed, then it is easier to separate them. So over here, the relative volatility will increase. Similar to the furfural just now. So instead of the boiling point between 78 and 100, now you have between 78 and 120. Okay, so perhaps you can set the temperature of this distillation column at perhaps 90 degrees C. So it won't boil the water, but it will vaporize the ethanol. Okay. Yeah, I move to another example, which is the adsorption and stripping. Adsorption over here to separate the CO2 from combustion product in vapor phase, gas phase. So here you have CO2. Okay, here the MSA, the agent is the ethanol amine, EA. To absorb the rest of the gases and release only CO2. What is the combustion products other than CO2? What do we have? Water, you can have you have N2 as well. Okay. Perhaps other things are NOx, SOx. It depends to your fuel again. Okay, so the main focus over here is to separate the CO2. It used the ethanol amine as the MSA in liquid form. So the EA will absorb all those gases apart from CO2. So it will release only CO2. Okay. Now next one is stripping. Stripping the vapor. Here, a removal of light ends from naphtha, kerosene, and gas oil. So it uses MSA in vapor form. It will absorb the required component and release in the vapor stream over here. So here MSA plus the products. Okay. Can. Okay, next class onwards, I think you will start to involve some calculation. Some calculation on the separation, distillation column. Okay, so I will stop over here first. Please make sure you go back to understand the concept of this. Okay, so that's all for today. Thank you.